Objective in this project is to evaluate the potential of rice bran as a natural soil stabilizer. Second, to determine and compare the attribute limit of untreated soil and the soil treated with rice bran. And the last one, to align engineering practice with sustainable development goal in SDG 4 and SDG 5. In civil engineering, wheat or nature fine-grained soil such as clay and silt frequently present the geotechnical challenge due to their unfavorable physical properties. This soil exhibit a low bearing capacity and high swelling shrinkage potential when exposed to moisture. If left untreated, constructing on such problematic subgrades can lead to infrastructure damage, including the cracking of building foundation, severe road pavement settlement, and abutment failure. To overcome this limitation, soil stabilization is essential to exchange the soil strength and engineering durability. While traditional stabilizers like chemical cement and lime are widely used, their production is costly and release significant carbon emission. Therefore, this project introduced a sustainable alternative by utilizing rice bran as an eco-friendly recycle stabilizer.
Alphabet test procedure. Step 1. Soil sampling and preparation. Prepare a dry raw soil sample of sufficient quantity to ensure that enough fine material can be extracted for the subsequent testing phase. Step 2. Sieving process. Sieve the prepared soil sample through a 0.425 mm test sieve to isolate the fine-grained particles. Only the soil that successfully passed through this sieve sieve will be utilized for the attribute limit test. Step 3. Apparatus setup. Arrange all required equipment on the laboratory workbench. This include the flat glass plate, spatula, plate knife, moisture can, a wash bottle filled with distilled water, a weighing balance, and the compenetrometer apparatus. Label and record the initial mass of the empty moisture can. Step 4. Mixing the soil paste. Place the sieve soil onto the flat glass plate, then add distilled water gradually. Carefully mix the specimen using palette knife until it transforms into a thick, smooth, and completely homogeneous paste with no trapped air pockets. Step 4. Plastic limit testing. Take a small portion of the mixed soil paste and form it into a ellipsoidal mesh. Roll the mesh between your fingers and the glass plate at approximately 90 strokes per minute until the soil strip reach a uniform diameter of about 3.2 mm and begins to scramble under the rolling pressure. Gather this scramble portion into a designated moisture can. Step 6. Liquid limit testing. Press a portion of the remaining mixed soil paste into the penetrometer cylinder cup, ensuring a smooth, level surface. Lower the penetration cone assembly so the tip just touches the soil surface. Release the cone for exactly 5 seconds and record the diagraph reading to determine the depth of penetration. Step 7. Sampling and overdrying. Extract soil moisture sample approximately 10 grams from the test area of both the plastic limit and liquid limit setup. Place them immediately into label moisture can with their moist mass and place them into a drying oven at 105 Celsius for at least 16 hours to determine the exact water content. Water test procedure. Step 1. Soil preparation. The experiment begins with preparing about 3 kg of air-dry representative soil. Step 2. Sieve analysis. Any large chunks are broken down and the soil is sieved through a 37.5 mm or 20 mm sieve. Only the fine soil that passes through this sieve is collected and saved for the compaction test to ensure a uniform particle size distribution. Step 3. Initial water mixing. The sieve soil is placed into a large mixing tray. Distilled water is measured and added to the soil to bring its initial moisture content to approximately 7% or slightly less than the estimated optimal moisture content. Using spatulas, the soil is mixed smoothly until the moisture is evenly distributed throughout the batch and it is left for a short period to mature. Step 4. Portal mold and collar preparation. Before compacting the soil, the 1000 mm volume portal mold and its base plate are cleaned of any old soil debris, fitted together and weighed to record the empty mass as M1. A thin layer of grease is applied to the inner surface of the mold to minimize friction. Finally, the collar extension is securely attached to the top of the mold to prevent soil overflow during compaction. Step 5. Dynamic compaction in 3 layers. The mature soil is remixed. The operator then fills the mold and compacts the soil in 3 equal layers. For each layer, a standard 2.5 kg rammer with a controlled dropping height of 300 mm is used to apply exactly 27 blows evenly across the entire surface of the soil layer. Step 6. Surface trimming and bulk mass determination. Carefully detach the extension collar using a steel straight edge to trim and shave off any excess soil protruding above the rim until the surface is perfectly flush with the top of the mold. Next, clean any loose soil from the outside surface of the apparatus and weight the mold containing the compacted soil to record the bulk mass M2. If available, test the penetration resistance on the compacted surface using a proton needle at this stage. Step 7. Moisture sampling and test interaction. Push the soil out of the mold using a sample extruder and collect a representative specimen from the settle core for over-drying water content determination. Repeat the entire compaction sequence step 3 to 6 about 6 times, adding gradually increments of water to the soil batch each time until the total mass begins to decrease due to saturation. Second attribute test by using 5% raspberry additive from soil. Step 1. Material preparation and drying mixing. Prepare the material. Air dry the soil sample and sieve it through a 0.4 to 5 mm mass. Ensure the rice bran is dry and finely sieved. Portion and mix. Weight the soil and rice bran according to the designated 5% weight proportion. Fully dry, mix them on a glass plate until the mixture is completely homogeneous. Step 2. Wet mixing and curing. Add water. Gradually add distilled water to the dry mixture while mixing continuously with a spatula. Achieve consistency. Work the mixture until it forms a thick, elastic and homogeneous paste free of air pockets. Cure the sample. Place the paste into a airtight container and let it cure briefly. Step 3. Plastic limit testing. From the treat, take a small portion of the paste and roll it using your finger on a glass plate. Observe scramble. Continue rolling until the face forms a treat of a uniform 3.2 mm diameter and just begin to scramble. Collect sample. Gather the scramble treat piece to use as the plastic limit test sample. Step 4. Liquid limit testing. Cone penetrometer method. Prepare the cup, fill the remaining paste into the cup of the cone penetrometer and smooth the top surface. Calibrate the cone, lower and adjust the 80-gram steel cone so that its tip just touches the smooth surface of the paste. Jerk penetration. Release the cone mechanism for exactly 5 seconds, then record the penetration depth shown on the diagram. Step 5. Moisture content determination. Weight wet mass. Immediately place the collected specimen from both the plastic limit and liquid limit test into separate moisture cans and record their weight mass. Overdry. Place the cans in a laboratory oven at 105 Celsius for at least 16 hours. Final measurement. Remove the sample, weigh their dry mass and calculate the actual moisture content for both limits. Second, photo test by using 5% rice bran additive from wet soil. Step 1. Material preparation. Sieve and weight. Prepare approximately 3 kg of air dry soil sieve through a 3 mm or 37.5 mm mesh. Dry mixing. Add 5% rice bran by dry weight of the soil and mix thoroughly until the mixture is completely homogeneous. Initial moistening. Add distilled water to achieve an initial moisture content roughly 7% below the estimated optimal moisture content. Maturation. Allow the mixture to mature briefly for uniform moisture distribution. Step 2. Equipment setup. Initial weighing. Clean and weight the empty bottle mold attached to its base plate. Lubrication. Apply a thin layer of grease to the inside of the mold or facilitate sample extrusion. Assembly. Securely attach the extrusion collar to the top of the mold. Step 3. Compaction process. Layering. Divide the soil rice bran mixture into 3 equal portions. Compaction. Compact the soil in the mold in 3 equal layers. Blow. Subject each layer to 27 uniformly distributed blows using a 2.5 kg rammer dropper from a height of 300 mm. Step 4. Finishing a wet mesh measurement. Trimming. Carefully remove the extension collar and trim the excess soil flush with the top of the mold using a steel straight edge. Final weighing. Wipe the outside of the mold clean and weight the mold containing the compacted soil. Step 5. Moisture content sampling. Extrusion. Push the compacted soil cylinder out of the mold using a sample extrude. Sampling. Extract a representative soil sample from the core center of the extruded specimen. Overdrying. Dry the sample in an oven at 105°C for a minimum of 16 hours to determine the moisture content.
Moving on to our standard photo result test, let us look at the compaction curve for both the untreated and treated soil sample. For the untreated control soil, the graph shows a maximum dry density of around 0.55 megagram per cubic meter at a very low moisture content of about 1.12%. As more water is added, the dry density drops sharply and level off at a lower density. Now, when we look at the soil treated with rice bran, the compaction curve shifts significantly. The maximum dry density drops to around 0.09 megagram per cubic meter, which occur at a moisture content of roughly 13.6%. As the moisture content increases further toward 58%, the dry density steadily decreased to 0.03 megagram per cubic meter. This reduction in dry density steadily decreased to 0.03 megagram per cubic meter. This reduction in dry density happened because rice bran is much lighter than soil particle, which increase the optimum moisture content need for compaction. Now, let us discuss our lab finding. Adding rice bran clearly changed how the soil behaves. In the ultimate limit test, the plasticity index went down. This showed that rice bran helped reduce the soil swelling and shrinkage when it gets wet. In the compaction test, the dry density become lower, while the water content become higher. This is because rice bran is much lighter than natural soil. Replacing heavy soil with light rice bran lower the overall weight. Also, rice bran absorb more water, so we need add more water to compact the mix properly. To get accurate result, we took clear precaution. We made sure the soil strip were rolled to exactly 3 mm for the plastic limit test. We also ensure the rammer drop freely without any friction during compaction. This simple step help us reduce error and get more data. In conclusion, we successfully achieved all our project objectives. we managed to evaluate the soil's engineering properties and analyze how adding rice bran changed both its compaction and plasticity. However, some human error did occur during our lab tests. For example, there were slight inconsistencies when rolling the 3mm soil treat for the plastic limit test. We also faced minor friction during the manual convection blow in the standard proto test. These small errors might have slightly affected the precision of our final optimum moisture content and dry density readings. To improve future research, we highly recommend two things. First, we should run the unconfined compressive strength test (UCS) to directly measure how much stronger the treated soil become. Second, we should experiment with different sizes of rice bran, or even use rice bran ash. This will help us to see if a finer ash can trigger better chemical reaction to achieve a higher dye density. Beyond the classroom, this project offers great practical benefit. Environment use agricultural waste like rice bran keep it out of landfill and stop open burning, turning tests into a valuable engineering resource. Economical, it is a cheap and easily available alternative to expensive stabilizer like cement or lime, making it perfect for low volume rural road. Ultimately, proper soil compaction and stabilization will prevent road cracking, landslide failure, and foundation settlement, lead to highly sustainable infrastructure. Best for all, this hand-off teamwork successfully turned complex soil theories into the real-world solution.